Example 3 is pretty similar to what we were doing in examples 1 and 2, just asking for some numbers, basically one at a time in this case. It says a stone which has a weight of 7.35 newtons experiences a force of 90 newtons straight upward. Determine the mass. Well, let me draw the picture here. Here's my stone. It has a weight. Now remember, weight is force due to gravity. So force due to gravity, 7.35 newtons. It experiences a force of 90 newtons upward. So the applied force in this case, 90.0 newtons. What we want to do is we want to figure out the mass of the stone. Well, mass can be figured out if you know the force due to gravity. Remember, force due to gravity depends on the acceleration due to gravity. The acceleration due to gravity on Earth is constant, 9.81 meters per second square. You go off the planet, the acceleration due to gravity will change, therefore your weight will change. I weigh about a sixth of the amount on the moon as I do on Earth. Doesn't mean I lose mass, my mass stays constant, but I actually have a less force of gravity on the moon. That's why when people hop along the moon, they're not really hopping because they're happy. They're actually walking, but because the gravity is so much less, their steps seem to be a much longer because it takes them longer to come back down. So if we want to find the mass of the stone, we can use this formula off our sheet. Acceleration due to gravity is equal to Fg over m, I think is how it's written on your formula sheet, or Fg equals mg. So we could manipulate this formula, which we'll do on the right hand side here, as mass equals to Fg divided by acceleration due to gravity. We know the force due to gravity. This one is irrelevant to the net force. We're not using net force in this question. We're using force due to gravity. So it's 7.35 newtons divided by 9.81 newtons per kilogram, which is the other units for acceleration. Well, 7.35 divided by 9.81 should give us 0.749 to 3 significant digits kilograms. That's the mass of this stone. Now again, if we want to figure out net force, this is where you need the diagram. Since the applied force is in one direction, the weight is in the opposite. Notice it didn't tell me what direction the weight was. Weight always acts downwards to the center of the planet that you're standing on. So its force due to gravity will always be downwards. So if you wanted to find net force, again, the net force is going to equal to the applied force, because they're in opposite directions, minus the force due to gravity. If you put your numbers in there, net force equals 90.0 newtons, subtract 7.35 newtons, the net force equals 82.7 newtons. And really, to be specific, I should say upwards in this question, because it really doesn't tell us that it's only asking for magnitude. So I should be stating a direction in this case. It is going to accelerate upwards, and it's going to accelerate very quickly upwards because there's a large difference in those forces. And again, if we go back to the formula we used in example 1 and 2, we also know that F net can be equal to mass times acceleration. So acceleration will be equal to F net divided by mass. Put your numbers in. 82.7 newtons divided by 0.749 kilograms. And we go 82.7 divided by, I still had the original answer on my calculator. And again, to 3 significant digits, I get 110.38. So it should be 110 meters per second squared, or again 110 newtons per kilogram. And again, this should also be, because it is a vector, we should be stating a direction. This thing's going to accelerate upwards very quickly. Actually, 90 newtons is quite a bit of force, especially on a fairly light object like that. So again, very similar. This one just kind of used another formula in there, the FG formula. Remember, the formulas that we're talking about are either going to be forces due to gravity or forces due to friction, forces on a spring, I think are on that list, and then some sort of combination of different forces where you need to find a net force. Most important formula for forces that you'll see in this course is this net force. And if you understand that when you draw a diagram, when you have multiple forces, the net force is going to be basically the vector sum, meaning you'll either add or subtract those vectors to find the resultant or net force.